126 years. That is the age of the old colonial infrastructure that had long defined the landscape of Kenya. Why did the construction of a new railway require an investment exceeding $3,800,000,000? While it may seem like a simple replacement of old tracks, the engineering involved represents a complete technological leap for the continent. This massive financial and technical mobilization was necessary because the standard gauge railway was designed to handle high-speed transport across terrain that the previous narrow tracks could never navigate. China introduced a new wave of industrial development to the region by deploying advanced engineering systems and heavy machinery on an unprecedented scale. One can notice how the kilometer-long viaducts rise above the open savannas, creating a level path for trains over uneven ground. But this is just the beginning. The project required the mobilization of over 25,000 local workers and thousands of engineers who operated heavy hydraulic cranes and automated track-laying machines. It only looks obvious to build on flat land, but in reality, the geography of Kenya demanded the construction of hundreds of bridges and several deep tunnels. The camera glides along the elevated tracks, which ensure that the railway does not interfere with the natural migration of local wildlife. It is visible how the concrete pillars are sunk dozens of meters into the earth to stabilize the immense weight of the freight trains. The process is only gaining momentum as the new infrastructure connects the port of Mombasa to the interior. Sophisticated operating technology, which had never been utilized on such a massive scale in Africa, was integrated into every kilometer of the line. Because the system utilizes the international standard gauge, it allows for significantly higher speeds and a much larger cargo capacity than the previous colonial-era tracks. This strategic shift in engineering allows for the movement of millions of tons of goods annually. Transition to the next level. The heavy machinery and precise logistics systems now form the backbone of a network that aims to fundamentally reshape the economic trajectory of the entire East African region. At first glance, the massive investment appears to be a purely logistical endeavor, but in reality, it is a complex intersection of international finance and long-term geopolitical strategy. Billions of dollars were funneled into the procurement of high-grade steel and the deployment of digital signaling systems that monitor train movements in real time. Equipment gradually transformed the landscape, turning remote areas into hubs of activity during the construction phase. Everything only gets more complicated when analyzing the motivations behind such a massive commitment of resources. Large-scale infrastructure projects of this magnitude are built with a vision that extends decades into the future. From the initial drilling of bridge foundations to the final placement of the rails, the project represents a complete overhaul of the regional transport logic. The material and technology integrated into the soil of Kenya now serve as a permanent link between the coast and the heart of the country. Thus, the engineering phase concludes, leaving behind a functioning system that is ready to move into a new era of industrial operation. 480 kilometers is the total length of the modern transport artery connecting the coast to the interior of the continent. Why did this massive infrastructure project become a necessity for the region? At first glance, the existing transport network seemed functional, but in reality, the legacy of British colonial rule had deteriorated into a state of severe decay over many decades. Transportation costs from the port of Mombasa into inland East Africa had risen to become among the highest in the world as trains operated at a slow and inefficient pace. China proposed the construction of a modern railway network under the Belt and Road Initiative to fill this infrastructure gap. Construction of the standard gauge railway began in the year 2014. This monumental undertaking was supported by a loan of approximately $3,800,000,000 from the China Exim Bank. The state-owned China Road and Bridge Corporation took full responsibility for the complex design, the physical construction, and the deployment of advanced technology across the terrain. One can notice how the equipment gradually transformed the landscape during this intensive phase. The process is only gaining momentum. In a period of less than 3 years, the segment from Mombasa to Nairobi officially opened in the year 2017. The infrastructure was not delivered in isolation, as it arrived complete with Chinese locomotives, sophisticated signaling systems, and specific technical standards. One can notice the transition of knowledge through comprehensive workforce training programs that were transferred alongside the physical hardware. It gets more complex further on. China's interest was not centered on achieving short-term profit despite the investment of billions of dollars. The loans are structured to generate financial returns over many decades, serving a long-term strategic vision. It is visible how Chinese companies secure vital overseas projects while simultaneously exporting vast quantities of steel, heavy machinery, and specialized railway technology to international markets. This allows for the steady expansion of industrial output beyond domestic borders. Everything only gets more complicated as as the scale of the operation increases. But this strategic movement was not limited to the simple act of laying tracks and sleepers. In reality, the project served to build deep economic influence and robust supply chains within one of the fastest growing regions on the planet. The camera glides along the polished rails that now represent a significant geopolitical presence. Thus, the material and technological export creates a foundation for a presence that spans generations. The modern railway serves as a permanent link in the global production chain. 472 kilometers is the total length of the railway line stretching from the coastal port of Mombasa to the capital city of Nairobi. Why did engineers spend months analyzing the landscape with satellite data and aerial survey aircraft before a single shovel touched the ground? Planning such a massive corridor requires understanding every geological obstacle to ensure the most efficient path. This meticulous survey work allowed specialists to minimize environmental impact while reducing the overall construction costs of the project. It only looks obvious to draw a line on a map, but in reality, the terrain dictates every move of the heavy machinery. Modern measuring equipment confirmed that most sections of the line would require elevated railway structures. These viaducts provide a stable foundation that allows trains to operate continuously across diverse and uneven terrain. But this is just the beginning. The next challenge involved reshaping the entire construction corridor to eliminate the natural irregularities of the Kenyan landscape. Hundreds of bulldozers and grading machines moved into position to cut down high mounds and fill in lower depressions. The equipment gradually removes layers of earth to create a balanced surface capable of supporting massive construction loads. One can notice how the blades of the graders scrape the ground with centimeter-level precision under the constant supervision of surveying teams. The process is only gaining momentum. Specialists must continuously measure elevation and slope to maintain the required accuracy across dozens of kilometers of natural terrain. Excess sand and soil are transported away from the site by heavy trucks and automated conveyor systems. Therefore, the result of this stage is a perfectly flat construction zone ready for the critical compaction step. Why did the loose sandy soil require the addition of controlled moisture after the leveling was complete? At first glance, adding water to sand seems counterintuitive for stability. However, the liquid allows the sand particles to bind together more tightly, forming a much denser base than dry material alone could provide. Groundwater is evenly sprayed across the site using long spraying arms and dedicated pipelines to ensure the moisture penetrates deep into the lower soil layers. Everything only gets more complicated as the stabilization continues. Once the moisture levels are optimal, cranes equipped with steel weights weighing tens of tons move into the area. This technique, known as dynamic compaction, involves repeatedly dropping the massive weight from a significant height to create a powerful compressive force. One can notice how each impact sends vibrations through the earth, forcing the underlying layers of soil to lock together. Immediately after the heavyweights finish their work, steel drum rollers begin moving back and forth across the surface. The deep rumble of the equipment echoes as the rollers eliminate air pockets and solidify the foundation. It is visible how the soft, loose soil transforms into a uniform and hardened platform under the weight of the machines. The process does not end at this stage. By the time the surface dries under the sunlight, the ground has achieved enough strength to support cranes and concrete mixers. Following this, dump trucks begin unloading the characteristic red soil of the region to create a secondary base layer. Bulldozers push this new material over the stabilized sand to add even more weight and density to the structure. Heavy rollers once again traverse the site, compacting the red soil until it forms a solid and dense foundation. This reinforced surface is now capable of supporting concrete beams and columns weighing between 40 and 60 tons. These massive components are essential for the viaducts and elevated sections that define the new railway. On the reinforced and compacted ground, the project moves toward its next structural phase. 35 meters is the precise distance maintained between the massive concrete columns rising along the corridor of the line. Why are these supports positioned with such rhythmic standardization across the landscape? At first glance, the placement might seem like a simple design choice, but in reality, this specific spacing is engineered to maximize the stability of the viaduct while simultaneously neutralizing the physical effects of thermal expansion. These vertical piers reach heights of up to 15 meters and can weigh nearly 90 tons each depending on the specific terrain and the structural loads they must support. One can notice the surface of the columns, which are cast using specialized slip-form molds. The process is only gaining momentum as high-strength steel reinforcement is integrated into every pier. This internal skeleton ensures the concrete can withstand high temperatures, intense winds, and the relentless vibrations generated by the passage of heavy locomotives. Thousands of these concrete supports were constructed, forming long, straight rows that stretch across the plains of Kenya like a vast framework of steel and stone. The fabrication of precast concrete box girders represents the next level of the construction sequence. Inside specialized yards situated near the site, steel molds measuring between 30 and 32 meters in length are assembled with mechanical precision. It gets more complex further on as reinforced steel cages and intricate pre-stressing cable systems are lowered into these molds. High-strength concrete is then poured into the forms and vibrated continuously to eliminate trapped air bubbles. Each girder, weighing between 70 and more than 100 tons, is removed from its mold once the hardening process is complete. The equipment gradually moves these massive components to storage yards, where they await transport. It seems simple to move such weight, but in reality, the logistics of handling thousands of these units requires constant coordination. 30 meters is the average length of the spans that must be hoisted into the air. How do engineers lift such immense weight to the top of the 15-meter piers? Heavy lifting cranes or specialized launching gantries, which are massive beam installing frames that crawl along the bridge piers, are utilized to elevate the girders. One can notice how the gantry maneuvers, lifting each dozens of ton segment to a height of several tens of meters before positioning it. Precision is maintained within tolerances of just a few millimeters during the placement onto the bridge bearings. Transition to the next level occurs once the girder is temporarily secured by the engineering teams. High-strength steel tendons are threaded through the body of the girder and tensioned using heavy-duty hydraulic jacks. This creates internal compressive forces that allow the entire bridge span to function as a single, continuous, and stable concrete structure. Everything only gets more complicated as the final sealing of the structure begins. A specialized concrete grout or mortar is injected under pressure into the cable ducts to protect the steel tendons from the threat of corrosion. The next girder is then lifted and installed using the same repetitive and precise sequence. One can notice how each span links together like the links of an enormous structural chain. In a span of just a few hours, a viaduct section stretching dozens of meters is fully realized. As thousands of these girders are assembled, the elevated railway slowly takes its final shape, extending its reach across the vast plains of East Africa. The structural backbone of the modern line is now firmly established across the horizon. 1,200 degrees is the temperature reached inside the massive industrial furnaces of the rail manufacturing plant. Why is such an extreme thermal environment maintained before the rolling process begins? At first glance, the steel blocks seem indestructible, but in reality, the heat must penetrate the entire mass of the metal to make it malleable. This intense energy softens the heavy steel billets and blooms, which are stacked in long rows within the raw material storage area, each weighing several tons. The process is only gaining momentum. Overhead cranes and automated conveyor systems move the steel blocks toward the furnace. One can notice how the metal glows with a blinding intensity as it absorbs the heat. The equipment gradually transitions the material from the furnace directly into the rolling mill. 1,000 to 1,100 degrees is the specific temperature range maintained as the actual shaping of the railway rail begins. At this stage, the steel is soft enough to be stretched and formed under enormous pressure from the machinery. The billets pass through a long series of rolling stands, each equipped with specially designed steel rollers that gradually squeeze and elongate the metal. One can notice how the thick rectangular billet becomes longer and thinner with every pass. Precision machined rollers create the three key parts of the railway rail during this transformation. The head is formed to support the train wheels, while the web is shaped as the vertical section that distributes the load. Finally, the foot is pressed into a wide base that anchors the rail to the sleepers. During this rolling process, the steel can extend from an initial billet just a few meters long into a rail that measures up to 100 meters or more in length. Powerful motors control the speed of the rollers to ensure the metal flows evenly. Sensors continuously monitor temperature and alignment to prevent any deformation. Sparks, heat waves, and the thunderous sound of machinery fill the rolling hall as each glowing steel beam is stretched into its final shape. The camera glides along the cooling racks where the metal lays in an even layer. By the time the rail exits the final rolling stand, it has already taken on its precise geometric profile. Transition to the next level. Controlled cooling and straightening must occur before the rails are cut and prepared for installation. But the rail itself is only one part of the structural system. Another critical component is still needed to ensure the stability of the entire railway. Concrete sleepers provide the necessary foundation. These concrete blocks sit directly beneath the rails and are responsible for maintaining the correct spacing while transferring the weight of passing trains down to the track foundation. It gets more complex further on. 2.5 meters is the approximate length of the steel molds used to produce high-strength, pre-stressed concrete sleepers. Before the concrete is poured, pre-stressing steel cables are tensioned inside the mold with calculated force. This allows the hardened concrete to achieve a greater load-bearing capacity and improved resistance to cracking. Once the concrete reaches the required strength, the sleepers are removed from the molds. One can notice the installation of elastic rail clips, steel base plates, and fastening bolts. Everything only gets more complicated. 300 kilograms is the maximum weight a single sleeper typically reaches during production. These units are installed at intervals of about 60 centimeters along the track. 1,600 to 1,700 sleepers are required for every single kilometer of railway. Their main function is to distribute the weight of trains evenly onto the ballast layer and the subgrade below. This ensures the precise distance between the two rails is maintained for decades. The components are now ready for transport to the construction site. 20 to 25 concrete sleepers form the foundation of a single modular track section. Why are these components joined on a specialized assembly platform rather than directly on the railway bed? It seems simple to assemble parts on site, but in reality, factory-level precision is required to ensure the structural integrity of the entire line. By pre-assembling the modules, engineers achieve a level of geometric accuracy that is impossible to maintain under varying field conditions. Long steel rails, frequently reaching lengths of tens of meters, are lowered onto the steel base plates with calculated movements of the overhead manipulators. Workers then drive elastic rail clips and anchor bolts into the sleepers, locking the steel into its permanent position. The process is only gaining momentum. Once the fasteners are tightened, the structure, measuring between 12 and 15 meters, transforms into a single rigid unit capable of withstanding the stress of heavy lifting. One can notice how heavy cranes or specialized track lifting systems hoist these 12 to 15 meter sections off transport wagons. The equipment gradually lowers the modules onto the prepared ballast layer or concrete bridge decks. It is visible how the metal lays in an even layer against the foundation. This modular installation method allows the construction of the railway to proceed at a significantly higher speed than traditional methods. 1,435 millimeters is the mandatory standard gauge distance that must be maintained between the two rails. At first glance, aligning these massive sections seems obvious, but in reality, every millimeter of deviation could lead to catastrophic wear. Each module is guided by hand and machine until the alignment is perfect. But this is just the beginning. When two adjacent segments are positioned correctly, the gap between the rail ends must be eliminated to create a continuous path. The camera glides along the joint, where workers prepare for thermite welding or specialized electric welding. This process creates a seamless connection, which is essential for reducing high-frequency vibrations and increasing the long-term durability of the metal. Everything only gets more complicated as the weld is inspected for internal defects. The equipment gradually grinds the cooling weld until the surface is perfectly smooth to the touch. Once the joint is cleared, the final tightening of the clips and bolts onto the sleepers ensures the structure is immovable. Additional modules are installed in this identical sequence, one after another, as the continuous steel line stretches across the landscape. The process does not end at this stage. Tens of thousands of sleepers and hundreds of kilometers of rail gradually coalesce into a massive transport system. One can notice the scale of the engineering effort as thousands of concrete pillars support the route across the plains of Kenya. The project is more than a simple assembly of materials. 472 kilometers is the total length of the Mombasa to Nairobi standard gauge railway. Construction of this infrastructure began in 2014 and reached completion after nearly 3 years of continuous labor. $3.8 billion was the total investment required to finalize the massive undertaking. This reflects the immense scale of the design, manufacturing, and construction phases. It only looks obvious when the first train finally rolls along the finished steel tracks, but it represents the culmination of years of technical precision. The railway stands as a completed engineering achievement, connecting regions through a unified transport corridor. From the initial casting of concrete to the final welding of the rails, every stage has been synchronized. The massive construction journey concludes as the infrastructure enters its operational life. The material is ready to serve the next generation of transport requirements without haste.